Okay, in today's video, we will discuss Lagrange's method to find extrema of functions of two variables or more variables, in fact, subject to a restriction, that is, on top of a curve. Okay, so this is Lagrange's method. Okay, the question is the following. Let us recall what the question was. Okay, given a function, I will not here worry about the nice properties of the function required, namely it should be differentiable and so on, but for the time being, okay, just given a function, okay, find its minimum and maximum values, okay, on top of a curve in plane, okay, h of xy equal to 0. This is the basic question. Okay, I always write on top, but of course it should be below the xy plane. That's not the question. Namely, when xy satisfy the equation of the curve, and I put those points in my function, which one is the biggest value? This is the question. Okay. Now, if the curve has corners, etc., or if it's not a closed curve, okay, like half a circle and so on, we have to consider the endpoints separately. So, if okay, the curve okay, has has points where no tangent line can be drawn, this includes all the bad cases, okay? We check those points separately. Okay. So this is not part of the Lagrange problem. So what we expect here is that this curve is a smooth curve, basically, like a circle or an ellipse. So the situation looks like this. Okay. At the bottom, okay, we have a curve given explicitly, and at the top, we have a surface. Now, when we look at the top, we reach a surface on the surface, a different curve, of course. Now, if we look at a point here and draw the tangent line. Okay. At the top, we will reach a point like this. Okay. And the tangent line drawn to this point will be perhaps, well, maybe make it something like this so it looks better. Will be something like this. Actually, I want to call this L, this T. Okay. Clearly, the tangent lines L and T have something in common. What is that? Well, suppose, okay, look at this curve, okay, and consider in both cases what this pink curve is. Okay. Now, gamma is, of course, something like this. If x of t, y of t, okay, is on L, call this gamma 1, is on gamma 1, then, of course, when I put them in the function, that is x of t, y of t, and f of x of t, y of t, okay, is on gamma. So if I take a point on the curve at the bottom, okay, and put it in the function, I get the z coordinate, but the xy coordinates are the same. So okay, this is the basic relation. Now, what about the tangent lines drawn to them? Obviously, we have the following. From our previous remarks, if we take the derivatives of the components, we get parallel vectors to the tangent lines. Okay, so assuming differentiability, I will not, as I said, bother about that at this point. Okay, so okay, by previous arguments, we already worked with this. Okay, the derivative x prime t, y prime t, okay, is parallel to L, okay, at any point. Okay, and so similarly, x prime t, y prime t, and z prime t, which of course is f of x of t, y of t, derivative, which of course is f sub x, x prime, plus f sub y, y prime, t. Okay, this is parallel to t. So from here we observe that the tangent line, a vector parallel to the tangent line L, okay, has on top of it this vector whose first two components are the same. So if we have, okay, a vector in plane which is parallel to L, a vector parallel to T is exactly on top of it, but with a z value, so they can look like this. Okay, one can have a positive or negative z component. But the first xy components are the same. Okay. Well, now let us start from the curve in plane. Now, h of xy is 0, and so this is a vector parallel to L. Okay, but we also have the following. Now consider, okay, a point, okay, on gamma 1. It is of the form h of, okay, then it satisfies h of x of t, y of t is 0. Actually, we did this before, but I'm repeating. So differentiating, okay, we have h sub x, x prime t, h sub y, y prime t is 0. Okay, so gradient h, which is hx, hy, is perpendicular to, well, this is just this dot product. Okay. And this is parallel to L, as we remarked. Okay. So L, any vector parallel to L, dot gradient H will be 0. So gradient H is always perpendicular to L, or any vector parallel to L. Okay. VL is any vector parallel to L. Now this is always true for a curve, a nice curve in plane. Now let us go back to the question we had. Well, this is standard calculations if we have differentiability of all functions included. Now let us look at the question, the problem. Okay, we want to find the minimum maximum values on top of this curve. Okay, now at such a point, because we don't have any corners, that's the assumption, then these maximum values will occur at a local extremum value, which means they will be critical points. So, okay, now, if P0, okay, is a point on gamma 1 such that, okay, minimum, respectively maximum, of gamma occurs, of course, that means on top of gamma 1. Assuming there are no corners, this is a local minimum or local maximum, hence a critical point. Okay. So its derivative must be 0. Okay. In other words, okay, its tangent must be parallel to the xy plane. Okay. Now, either way, okay, we then observe the following. So, at P0, okay, let us take the first one, the derivative. Well, what is the derivative there? Well, this derivative is the derivative of the function in the direction of VL. So at P0, okay, d VL f, okay, must be 0. Well, what does this mean? Okay, again, assuming differentiability, okay, this means directly gradient f at P0 dot VL is 0. Okay, actually, the unit vector, but it doesn't play a role because we have 0 here. Well, this, of course, means that gradient f at P0 must be perpendicular to VL. Okay. Again, equivalently, T is horizontal, that is, T is parallel to xy plane. So, okay, its z component, okay, so the z component of, let me see how I manage that, yes. So z component of any vector parallel to t must be 0. Okay, which is, okay, we just derived one example of such a vector. It was x prime, y prime, and then, okay, f1, x prime, etc., which is f sub x at p0, x prime t, plus f sub y at p0, y prime. Okay. So this must be 0. Well, this directly says that gradient f at p0 is perpendicular to the vector x prime t, y prime, which is parallel, okay, to L or parallel to VL. So what does this argument say? Well, it says that in general, okay, gradient h is always perpendicular to VL, to the tangent line at the bottom. Okay, but if we have a critical point at the top, the z component should be 0, which means that gradient f is also perpendicular to VL. Well, putting them together, so at p0, okay, the vectors gradient f at p0 and gradient h at p0 are both perpendicular to VL. Note that these vectors are all in the plane, not in space. Okay. And all vectors considered, okay, are planar. Okay, let me say are in x1 or okay. Well, what happens then in a plane? Okay, if you have a VL and two vectors, okay, perpendicular to it, gradient h and gradient f anyway, okay, they are both perpendicular. This implies that, okay, gradient h is parallel gradient f at p0. Now this happens if you have a critical point. Now this was Lagrange's observation. So what is the method? Well, to find all such critical points, we have to look for points p0 where these two vectors are parallel to each other. So, Lagrange's method. Okay. Consider all points, or rather, to find p0s such that gradient h at p0 is parallel to the vector here, gradient f, but parallelity means that one is a multiple of the other in plane. So, okay, it means that okay, one vector is a multiple of the other if you put it on the other side. Well, sometimes one puts a minus sign here, but there is no guarantee that lambda is positive. So it could be any number, any real number. Okay, and so this should be the case. Okay. Now, on the other hand, p0 is not an arbitrary point in plane. It is a point chosen from the bottom curve, h of xy is 0. So it must satisfy that. And h of p0 is 0. Okay. Now this system of equations, okay, where of course this lambda is called Lagrange multiplier, okay. We will not use that name too often. It's just given to honor Lagrange. Okay. Now, we want to find p-zeros which satisfy this set of equations. Now, how many unknowns do we have? Well, first of all, p0 is a point in plane, so it has two unknowns, x0 and y0. And lambda is not known, so we have three unknowns. Okay. So we have three unknowns, okay, x0, y0, okay, coming from p0, and lambda, this is our p0, and three equations. Because the first one is a vector equation. If you equate the components, you get two equations from there. Okay, three equations, two scalar equations from the vector equation, and one from H. Okay, H p0 0. Okay, so the system says solve. Okay. Of course, in this solution, we are not interested in lambda. We don't care what lambda is. Okay, but it is there. Sometimes in the solutions, as we will see, it is not a bad idea to solve lambda first, depending on the simplicity it brings to us. But we are basically interested in p0. We want to find p0 here. Or p-zeros. There can be more than one. Okay. Now, before we pass to examples, let me have a general remark. Okay, we can generalize this method. We can generalize it to three variables. Namely, we have f of x, y, z. Okay. This is to be minimized. And x, y, z are taken from a curve. Namely, okay, g of x, y, z is 0, and h of x, y, z is 0. Okay. Remember, these two equations tell us that we are talking about the intersection of these two surfaces. So, okay, this is a curve in space. Since intersection of two surfaces. Okay. Compare with lines. Okay. A line was intersection of two planes, so its equation was two equations. A general curve in space is the intersection of two surfaces, so it is equation of a curve in space is given by two equations. Okay. So question is, okay, find minimum maximum of f, okay, on top of the curve, okay, g is 0, h is 0. So this is just one dimension higher version. Okay, so what does all this say? Well, it says the following. Let me just explain first. Okay. Well, if we consider the curve which is given by these two surfaces, that curve lies on both surfaces. So its tangent line lies on the tangent planes of both surfaces. Therefore, okay, its parallel vector is perpendicular to both gradients. Okay, so let me just simplify this. Okay, now the curve, say gamma, which is the intersection of G0 and H0, has its tangent line, okay, on tangent planes to both surfaces at a given point, of course. So, okay, a parallel vector BT to this tangent line is perpendicular to normals of these tangent planes. Okay, so all this says that BT is perpendicular to, well, what are normals, okay, to these surfaces? Just the gradients. So we have that. Now, if, okay, we are at a critical point, if P is, or let me say P0 is a critical point, okay, well, the Lagrangian way, that is, it's a critical point on top of this curve, where, of course, because we have three variables in the fourth dimension, okay, then okay, it's the slope, or rather, the slope of its tangent line will be 0. So d, okay, Vt of f at P0 will be 0. So again, if differentiable, this will mean that we have gradient f at P0 dot Vt, okay, equal to 0. Well, this says gradient f at P0 is perpendicular to Vt as well. I will not spend much time on the geometry here because we cannot sketch it. It's in 4 dimensions. So, okay, we get at P0, okay, gradient H, gradient G, gradient F are perpendicular to Vt. Now, one difference, all of these are 3-component vectors. Okay, this happens, of course, at the critical point. Well, similar to the previous case, if you have 3 vectors perpendicular to Vt, this means that all three vectors are in a plane or parallel to a plane with normal VT. Okay. So, okay, gradient H, gradient G, and gradient F, okay, are parallel to a plane, okay, with normal VT. Now, if you have three vectors in plane, okay, then you can always write one of them using the others. Okay. So, okay, gradient F is, I will use minus lambda G minus mu gradient H at P0, of course, all the time. That means that, hence, okay, gradient F at P0, lambda gradient G at P0, plus mu gradient H at P0 is 0, 0, 0. Of course, this looks familiar from the two-variable case. We only have here the three-variable version. Okay. Now, what was P0? P0 was a point on the curve. So it satisfies, or it should satisfy, both surfaces G and H. Okay. And P0 is on both surfaces. Now, this says that H of P0 is 0 and G of P0 is 0. So this is the system. What does it say? We have three unknowns coming from P0. We have two factors coming from Lagrange's method. So we have five unknowns. And how many equations? Now, this is a three-component vector equation. So 3 scalar equations, 4 and 5 scalar equations. So, of course, we are not interested in lambda and mu. We are interested in x0, y0, and z0. Okay. So, solve, of course, you can solve all 5 of them, but we are interested in the point. So this is Lagrange's method, okay, in 3 variables. Just a remark, you need not have a curve, okay. The curve can be replaced by a surface. That is, if you don't have H, it's still okay. Okay. And finally, okay, these can be generalized. We will not do that. To functions from Rn into R. Okay. A last definition, or let me say terminology. Okay. Okay, one says, okay, minimize, maximize F subject to the restrictions which can be in 2 dimensions, H of is 0, or in 3 dimensions, G of this is 0. So these restrictions, okay, are also called constraints. This wording is used in defining a Lagrange problem. Okay. So now, let us pass to examples.